Problem 86. Here we have a block that's going to slide down a hill, end up in a valley, and then up onto a plateau. And you can probably guess what they're going to be asking at some point. But here are the points for which they want to know what the speed is. So it says here, what are the speeds at B, C, and then if it gets to D, or does it stop somewhere along that rough section L? So let's knock it out one point at a time. So I'm going to write down the equation of everything. Okay, gravitational potential at state 1, the kinetic energy at state 1, the elastic potential at state 1. Although we haven't seen a spring yet, we will. The gravitational potential at any of the other points. So let's say B will be my state 2. Okay, so I'm starting at state A, but I'm going to end up at state B. So that's what 1 versus 2 represents. Okay, are we still moving? I sure hope so. Is there a spring? Not yet. And are we losing energy due to heat? So that would be, I'll just use the letter Q, stand for heat. Do you know that to be Q is equal to the force of friction times the displacement. So that's a dissipative energy. All right. So for part A, so I'm above where I'm going to end up. So I'm definitely have gravitational potential energy. So that's going to be mgh1. I'm moving at A, so that's going to be 1/2 mv squared. All right, now I'm down the valley. So here I'm at B, and I'm the lowest point possible. Okay, so that's going to equal, that energy at A is going to equal the energy at B. And I'm at the lowest point. I'm moving, obviously. There's no spring involved, and I haven't dissipated energy due to friction. So this will be the 1/2 mv2 squared. So that's going to be the velocity at B for this part. All right. There's a mass in every term. Okay. I'm not going to substitute numerical answers, but I'm just showing you how I apply conservation energy. Thinking of this as state 1 and this state 2. All right. So we're going to solve for the velocity. So V2, your expression should look something like this. The square root, all right. See how I'm going to take the square root of both sides, but I'm going to multiply first by 2. So 2 times the stuff that's on the left-hand side. So GH1 plus 1/2 V1 state 1 squared. Okay. So that'll give you your velocity. Expect to get like 12.91 meters per second. Okay. What's the speed at C? Okay. All right. I'm going to refer to my equation of everything, and you take your pick. You can start at B and go up to C if you like. We can certainly do that, or you can start at A, pass B, and go to C. So state 1 is going to be A, and state 2 will be C. Okay. Let's try this. I'm going to think of B as my starting point in energy, and then I'm going to rise up to state C. Just to show you, it doesn't matter. Okay? Energy at any point, total energy at any point is equal to any of the other points. All right. So let's go from the standpoint of B. So we have it's just kinetic energy at B. So we have 1/2 m velocity at B squared is going to equal the energy at C. So now we're going up H2. So we're increasing our gravitational potential energy, mgh2. Okay, if I started at A, it would be H1, and then we're at H2. So you almost have too much algebra there. So do yourself a favor, simplify things. So mgh2, and then we're moving still. So that's going to be 1/2 m v, and I'll substitute this c because that's the velocity at c. Okay. Looks like we can cancel the mass in every term. Just know that you can. And let's solve for the velocity at c. Velocity at c is the square root. Okay, I'm just going to put that square root sign there. But before I'm subtracting GH2 from both sides. Okay, and then I'm going to multiply both sides by 2. So 2 times the quantity, 1/2 velocity at B squared minus GH2. All right, so that's the symbolic expression for the velocity at C. All right, and I'll give you the answer I got. I got 11.28 meters per second. Okay, now let's go C. Let's check out C. Does the block reach D? I don't know. Let's assume, okay, I'm going to take a guess again. I'm going to assume it doesn't reach D, which means it doesn't have kinetic energy at D. Okay, let's say you did solve for the kinetic energy or the velocity at D. You come up with, you would get negative kinetic energy. Now, can an object have negative kinetic energy? You're hearing this for the first time. No. What that means, if you apply conservation of energy and attempt to solve for the kinetic energy at D, you get a negative value. That means the particle, or the mass in this case, does not exist there. All right. So I'm going to take a wild guess that it doesn't reach D. So it lands somewhere in here. Okay. All right, so it's going to be somewhere, but we're not too sure. So let's start at C, because we know the kinetic energy, and we're not going to go up or down, not worry about it. But you could knock yourself out. You can start at A, just as long as you account for all the different forms of energy. A, we have kinetic and potential. Once we get to the plateau, I think we come to a stop. So take your pick. So that's just force friction times distance. All right, so let's see. Let's start at C. So we have kinetic energy at C, 1/2 mv sub c squared. All right. We don't have to worry about going up or down. So don't worry about a change in gravitational potential energy, because we've already arrived at C with the same total energy as we had at A or B, for that matter. All right. So that's equal to, and if I assume that it's going to come to a screeching halt, then the energy is all dissipated. So all that kinetic energy that the block had is now dissipated in the form of heat. All right, so that's going to be mu kinetic mg, and we don't have to worry about cosine theta this time because we're on a level surface, times d. All right. Now, masses cancel. Okay, mass cancels. And we're going to solve for the distance. So the distance is going to be vc squared over 2 mu kg. Okay, so that's our solve for the distance, that it ended up somewhere. Not the total length, but I'm assuming that it was short of that. So let's check it out. If you plug all this stuff in, the velocity at C that you got right here, and then square that, divide by 2 mu g, you're going to get 9.27 meters. Ooh. So in that case, it says that L is 12 meters long. All right, I guessed right. So the distance is less than the specified length, L. Okay. Check. All right. There's 86.